Okay, so this is your unit 4 of your module 3, torsion. This will be the last unit that we will be discussing about torsion. Okay, so this topic is about helical springs. Okay, how is that helical spring related to torsion? Okay, so in this unit, these are your unit learning outcomes. Familiarize with the formula for the maximum shearing stress in helical springs. Familiarize with the formula for the elongation of helical springs. And then incorporate helical springs in statically indeterminate members. So isn't it we discuss about analysis or yes, analysis of your statically indeterminate members. And then before we only had there that the additional support is rod, tension rods. And then this time instead of those we might be introducing springs so that we will incorporate these springs for your indeterminate members. Okay. So helical springs. So you can read about this. Okay. This is about your springs. Helical spring. So again, if you say helical spring, that is actually a spring. Of course, you know what is a spring. This is actually in the form of a circular shape. Okay, that is actually it is a wire. Okay, a wire that is formed in that shape. Helix in the shape of helix. So if you'll try to look at this top view, this is a circular shape. Okay, and then that is because that is due to the circular pattern of the wire. Okay, and then this distance from the circle on the top to the next circle of the circular rings, we call this one the pitch. Okay, the pitch of the spring, and then the entire length of that is from the top to the bottom. Okay, and then the angle actually of this one of this inclination going to the next circle is the coil angle, that is the alpha, but actually that doesn't matter. We will not be focusing on that on this unit, but that is how what we call this angle here, the inclination. And then of course the diameter, that is important, the diameter of the wire used to create this helical spring, that is important. Okay, because that will determine the strength also. So you can read about this helical spring in this description here. By the way, this helical spring is actually made by turning this wire, okay, which are actually compressed. This is originally compressed, okay, in the shape, and it is wrapped around on a circle. And then once that will be released, and that's the time you will be having this pitch, okay, because of the expansion of material. So initially, the angles, okay, the deformation here or the analysis is that we can actually simplify the analysis by considering that the angle here is very very small. Therefore, that could be considered as a circle. If I will consider one circular part, okay, that is a plane circle. So that is to simplify the analysis of your helical spring. So maximum shearing stress on these helical springs. Okay, by the way, how do we end up here with a shear stress? Okay, if ever I will try to elongate, I will try to stretch this helical spring. What happens? Okay, this will elongate, and then the dimension of the circular pattern of that will be reducing, isn't it? And then just imagine the particles of this wire, the particles of this wire, what will happen? To resist the tension, it is not perpendicular since the cross-sectional is not perpendicular to the load. Isn't it? So the particles of this will experience a shear to resist the rotation of this spring, because as you will try to elongate or compress that one, there is this adjustment of your diameter here, okay, and the adjustment of that will actually cause a rotation on the wire itself. Okay, the adjustment of the entire outer diameter of the helical spring will actually cause. Okay, if you try to stretch that one or compress, the adjustment of the diameter will actually cause the material to twist or the wire to twist. So again, the same. That is why this helical spring is included in your torsion. So your wire itself there will experience a torsion, and if there's a torsion, there's a shear. Okay. So maximum shearing stress on the helical spring. Okay, I will just give you directly the formula. I will not, of course, give you the derivation because that is actually complicated. okay, and it will actually complicate the matter. So our focus here is actually to understand the formula and to use this one on a certain problem. So this is the shearing stress. Okay, so this is derived into this form, which is 16 PR over pi d3. Okay, the same thing. The bigger letters, if we are referring to diameter and radius, we are referring here to the dimension of the helical spring. Just like in your bolt, okay, the bigger R and D refers to the bolt circles. In here, the bigger R and D, that is the radius and diameter of the circle of the helical spring. But the small d and small r, that is the dimension of the wire used for the helical spring. Okay, and then multiply this one by 1 plus d over 4r. Okay, so this is again derived. If you want to know about the derivation, you can go to the book. Okay, you can go to the books and then find out the derivation of helical spring. And actually, you can find that one online. Okay, there is a derivation. You can research on that. So this formula neglects the curvature of the spring. So as I've said, since we will try to simplify this one by analyzing that this is a perfect circle, but actually there is a pitch for that, or there is a inclination or coil angle. But since again, since when we form this helical spring, these are close with each other. These are in contact with each other, and that is only having a pitch because that is already released. So again, this is considered to be circular. Cutting this one circle, complete circle, can be considered a plane circle. Okay. So neglect the curvature. Okay, this is used for light spring where the ratio is d, ratio d over 4r is small. Okay, helical springs. So P is the applied load, that is the actual load that will elongate your spring or compress your spring. And then your R is the mean radius of the helix. Okay, that is the shape of the helical spring itself. Right, the diameter divided by 2. And then your D there is the wire diameter, the wire being used in the helical spring. Okay. What else do we need to know is the deformation of a helical spring. That is your delta deformation. So how is the deformation of this? We are actually referring here to shear stress. However, the deformation that we are after is a distance or length. It is a length. Okay, it is a length, not an angle, not an angle deformation. So this is actually a distance deformation. So if ever I will apply a P, what is the elongation? If ever I will compress that one by P, what is the shrinkage or the contraction of that? So that is your elongation. Okay, it is a linear. It is not an angle. Okay, so 64 PR cube N over D4. Okay, what is the new variable here? PR and so on and so forth, it is used before. The new here is the N and J. N and G. Okay, the N is the number of turns. So that is the number of turns. Complete circle. Okay, 1, 2, 3, 4. So in case that is what we are finding here, the N number of turns for the helical spring. And then for your G, that is of course the rigidity, okay, modulus of rigidity of your material used in the wire. Okay, so by the way, okay, to relate this one, to relate this N with your deformation, okay, it is important for us to understand this one. If I will try to increase the number of turns based on the formula, okay, before we will go on the actual scenario, we are referring here to deformation, how much it will elongate. Okay, let's say that everything will be constant except for the n. Okay, if I will try to increase this n, what will happen? If I will try to put a big number in n, that will give me a higher value of deformation compared to a smaller value of n, considering that these are constant, isn't it? So relating that one on actual scenario, okay, isn't it? If you try, have you tried stretching a spring? Okay, if the spring is a short spring, it is a little bit hard for us to stretch and compress. It is stiffer. We call that one stiffer because we have what we call as the stiffness. Okay, but you will discuss that one on your higher subjects. Stiffness. Okay, the amount of deformation based on the strength of the materials. Okay, so stiffness. So the number of turns. So we are referring here to the number of turns and then the effect of that on the elongation. How much elongation? The bigger the turns, it means the longer your spring, it is easier for that to elongate under a certain P load, isn't it? You can relate that one to actual scenario. Considering a small spring, apply amount of force. Let's say that is 500 newtons. How much will that elongate? Compared to a longer version of that spring. Apply the same 500. Isn't it? That will give you a little bit longer deformation. It will be uh, it will be weaker compared to the shorter version of that spring. Okay, so the shorter the spring, the stiffer the spring compared to the longer of that version of that. So again, the number of turns will make your will reduce the stiffness of our spring. So the bigger the end, the bigger the deformation. So let's have an example. A helical spring is fabricated by wrapping a wire, okay, wrapping a wire of 3/4 inch in diameter around a forming cylinder 8 inches in diameter. Okay, so compute the number of turns required to permit an elongation of 4 inches without exceeding a shearing stress of 18 ksi, and then G is 12 times 10 raised to 6 psi. So that is the given for our problem. Okay, so the deformation is limited to 4 inches. That is required in the problem. The dimension of our helix is 8-inch diameter, so that will give us 4-inch radius. And then the diameter of the varius is 3/4 inch, and then the G for that certain material is 12 times 10 raised to 6 psi. And the allowable shearing stress for the type of material used in the wire is 18 ksi, or in pounds, since later on we will be dealing with those forces, and then we might be needing that. So I will multiply that to 1000. 1000 kips, I mean 1 kip is 1000 pounds. So that will give us 18,000 psi. So required is how many turns do I need for us not to exceed that 4 inches deformation. Okay. So these are the formulas. This is for the shear average shear stress of helical spring, and this is for the deformation of helical spring. So solution. Okay, play around with that. What do we have? Okay, based on what we have and based on the unknown, we will be using this. This is where we will find n. Play around with that. This is the formula. And then therefore, however, the point here is that yes, you have G, you have D, you have R, but we do not have P. We really need to find that P that will elongate that one to 4 inches. So we still need to go to your shrink. Okay. By the way, we will find the P that will elongate that to 4 inches at the same time. It will not exceed that 80. So, what's that? 18 KSI. So the point here is that I will be using all of the variables here except for the allowable. Okay, so maybe that will give me now an idea. How will I compute the P? Is to maximize your shear strength, okay, of the material used on the spring. Okay, so to maximize that, then I will be using the shear stress. So I will substitute the maximum, which maximum allowed, which is your 18 psi here. But of course, what we are trying to find is to get the equivalent P of that for us to use that in your solving for the n terms. Okay, since that is the only missing in our formula here. So again, rearrange this one. Bring out P. So this will go there on top together with your tau. This will go down together with your 16R. So that is our formula P. So we have here your substitute. Diameter is 3/4 inch. Tau. The allowable is 18,000. Okay, that is the reason why I converted this. Okay, so that I will have a force which is pound. But in case I did not convert this one, I will end up with a kips. Okay. So playing around and then calculating, you will have 357.07 pounds. That is the P for us not to exceed that 18 kips or kips per square inch, or 18 pounds, 18,000 pounds per square inch. Okay, PSI. So that is the P for us not to exceed that one. Therefore, that is the P that we will be using to solve for the number of turns for us not to exceed the 4 inches. So going back to what we derived, substitute what we need. Again, you need to transfer in case you have their variables, I mean units that needs to be transferred for us to have a cancellation. So you need to do that. So again, I will not be repeating how this is transferred again, how is this is cancelled. So, but you will notice here inch 4, so that will give you inch 5. Inch squared will cancel that. Inch 3, so inch 3 will cancel with that. And then pound cancel, so that is just a number. Okay, since we are referring here to a number or a constant. So there is no unit for that. So we ended up here with 10.413. Now, the question there, if you are forming a helical spring, there is no such as 10.4 turn. Okay? In case you will start the turning here, then that will end up to the same level or the same alignment with the end of the spring, isn't it? Unless that is twisted. So we might consider a whole number turns, okay, or whole number of turns. So the question then, will I make that 11 and not to exceed your 4 inches, or will I make that 10? So decide. And as I've said, that is why I emphasize this one. The number of turns will make your deformation or will make your spring. If I will increase the number of turns, that will make your spring less stiff, okay, or weaker. So that means that the lesser the n, the stiffer or the stronger your spring. Therefore, so instead of making that 11, that is wrong, because if I will make that 11, then that will make it a little bit weaker. So it will be exceeding a little bit your 4 inches, the allowable deformation. So what will I use is, I'd rather round it down to 10 turns. So 10 turns definitely will not be equal to 4, but close to 4, less than. Okay, less than 4 and close to 4. So it means it is maximized. Since again, we cannot measure the 10.413 turns. So I'd rather put it in a whole number, 10 turns. Or maybe you can say 10.5. Maybe you can measure the 0.5. But that type of decimal, you cannot do that. So maybe we can round it up, round it down. Again, that is the reason we are rounding down the n, because the number of turns will make, the bigger of that will make this one weaker. Okay, the smaller will make your spring stiffer. Okay, so that is for example number 1. Let's have one more. So this time we will now try to incorporate this helical spring into your indeterminate members. Okay, so a rigid bar pinned at O is supported by 2 helical identical springs. Okay, shown each spring consists of 20 turns, so your n is 20 for both of the spring. Your diameter for the wire used, the small d, is 3/4 inch, and then the mean diameter of the helix or the shape or the spring itself is 6 inches. 6 inches. So the radius of that is 3 inches. Determine the maximum load W that may be supported if the shearing stress in the spring is limited to 20 ksi. Allowable is 20 ksi or 20,000 psi. Okay? Required is the W. That will not exceed our allowable. So just like before, okay? If I will try to cut this spring, it's just like a tension or a supporting member. Okay? That might be under, but in this scenario, if this will be loaded, this will be stretched, that will be compressed, isn't it? Because of this pin here. So this will be under compression, that will be under tension. Okay. So now, if I will try to cut this support so that I will expose and then get a moment at O, because again, actually I do not need the reaction here. What we are going to focus is on the spring. Okay. So I will cut. I need to know the P being handled by each of these springs. So cut that one. That will expose your forces. But this one, since I've said that in this scenario, this will be compression, this reaction of your spring is going towards the membrane. This is away, since that will be tension. Okay, so if I am going to take a moment here at your okay, so if I will take a moment at your point O, then that will actually cancel out the reaction, so that we will not worry about the reaction here. So if I will do that, then this will be our equation. Let's say clockwise is positive, so this is counterclockwise 2 times P1 negative, counterclockwise 4 times P2 negative, and then this will be clockwise 7, 4 plus 3, 7 times W, equate that 1 to 0, equilibrium. Okay, so playing around and then solving for W, you will have here 2P1 plus 4P2 over 7. Okay, this will go positive on the other side. So just like on the discussion on the flange bolt couplings, um, the stress here is different from the stress there. Just like the stress on the bolt circles, okay? So if it says there that maximize your allowable, I will not input 20 here and then 20 there for me to solve for the equivalent W. No, I will not do that. Why? Because the scenario here is not the same. This might be stressed first compared to that or the other way. They will not be stressed the same manner at the same time. Okay, one will be stressed first before the other one. Okay, so I need to understand how the deformation and then the force P relationship of these two springs. Okay, so I will not just be using directly your 20 kips on the shear stress of these two. No. Okay, so two springs will not be subjected to allowable shear stress 20 kips at the same time. Okay, so from the deformation or deflection diagram, again, exaggerate just like in your temperature stress. Okay, just exaggerate for us to see that one. This will be your delta 1, delta 2, and that will be the displacement of the W. So at the end of that, let's say that this is rigid again. Consider that this is rigid. So the in these triangles, you can apply ratio and proportion. So delta 1 is to distance 2. Equate that one to delta 2 is to distance 4. I will actually not worry about that since that is not the unknown or that is not related to the problem. So this will be playing around with that. I can cross multiply. So delta 2 is twice your delta 1. Okay, so it means that the elongation, whatever the elongation of delta of your first spring, this is your first spring, multiply it to 2, that is the deformation of your second spring. Okay, so that means that if this is elongated twice this is more stress. Your second spring is stressed more than the first spring. So we can actually derive the relationship of the P being handled by that, because actually we are not after deformation, we are after your force P. Okay, since we need in your working equation for us to solve the W, the force P. So this is not what I will be using. I'd rather break this down again. Okay, going to the formula of helical spring, deformation of helical spring, your deformation is 64 PR cubed N over GD raised to 4, isn't it? So break this down, deformations, into that formula. The only difference is the subscript. It means that these are the two different springs. So what does that mean? However, in this one, so that this is not that complicated, since the type, okay, look at that. It is identical. It is they're identical. Okay, 20 turns. The dimension, the diameter is the same, and the diameter of the helix is the same. So your radius 1, radius 2 will be equal. So that will cancel out. The number of turns are the same. So N1, N2 is the same, cancel out. Your G is the same material. So G and G1 and G2 will cancel out. Diameter 1, diameter 2 is the same since you are using a 3/4 inch. So cancel out. So what will remain is actually, even your 64 here will cancel out. What will remain is 2 P1 and equal to P2. So that is what will remain in your complicated equation here. So that is now the relationship of our P1 and P2 for us to solve your P1, P2. But, okay, again, I cannot yet solve that one. I cannot pair it here. Since this is too unknown, you might be saying, I will pair it here. No, because in here there is additional unknown. So that is the final unknown. So I cannot do that. I'd rather find another equation to solve your P1, P2. Okay? So isn't it? What else did we not use? To maximize your 20 KSI or 2000 PSI. So I will go there. Maximize that one. Okay, play around with that. Bring out P. Everything is given. D, tau. Okay, the tau is this one. But later on, you will end up with the relationships because since again, I said that we cannot use the 20 KSI at the same time. So rearrange, you have the D, tau. We can figure out tau later on. R given, D given, R given. So that is what we will be using to solve your P. So this one, since this one first, since again we need to know your tau before we will go to P. So substitute it there, again, just like what happens here. Simple, but it will become complicated. Substitute, you will end up with this. However, again, due to the same type of material and the helix or helical spring, some of those will cancel. Diameter will cancel since they are equal. Radius will cancel. And if this diameter and radius are the same, this will be entirely the same as that. So actually, the entire denominator cancels. Your d cube cancels. Even your pi and pi cancels. So you're left again with 2 tau 1 equals tau 2. So, what's that? Again, the shear stress. Okay, based on this derived equation, shear stress on your second spring is twice the stress in your tau 1. So again, your second spring is more stressed. Therefore, where will I assume that 20? Is that on the second or the first? On the second, since that is the first to be stressed. So it means your tau 1 is smaller. But okay, in case you cannot figure that out yet by means of observation, you can try. Okay, let's say if I will say tau 1 is 20. Let's solve for tau 2. Okay, tau 2 is twice. So 40, which is already exceeding your 20 KSI. So that is not the case. Therefore, I will put the 20 KSI to your tau 2. Okay, near. I will put the 20 KSI to your tau 2. Therefore, solving for tau 1 divided by 2, that will be 10, which is correct. While your second spring reaches the 20 KSI, your first spring is still 10 KSI. So this is the first one to fail. Okay, the second spring. So again, this means that spring 1 will not fail, okay, prior to spring 2. So again, you have now your tau. Okay, go back here. You have now your tau. Go back there, solve for P1, P2, isn't it? So that is what we will be doing. You have your tau. This one, tau 1 is 20, 10 is this one. Forget about that. Okay, that is just a trial. Okay, tau 2 is 20, tau 1 is 10. Substitute in your P. You will have your P1 to be, okay, so the only difference in this P1, P2 is your tau. This one. Again, this is what we derived a while ago, isn't it? In here. So the only difference is that everything is identical except for the stress experience. So for the first one, first spring is 10, but in pounds PSI, okay, that will be 10,000. So your P1 is 259.87 pounds, and then change that one to 20,000 pounds per square inch, 519.75 pounds. Okay, so these are the P being handled by your springs, P2, P1. Okay, and then substitute, you will end up with the W. Okay, so that is the answer for this problem. Just actually the challenge here is the analysis. Okay, first and foremost, you should know how this system will behave. Okay, if that will be loaded, of course, that is compression. So I'd rather assume there a compressive reaction, because if you will cut this one and assume a tension, it's okay, no problem with that. But you might be confused later on if that will give you a negative P. Okay, it will give you a negative P and then negative tau. You might be confused about that, but the negative only means opposite direction. Okay, if you're referring to negative tau, that means it is tension, okay, or compression, or it is the opposite of what you assume. So again, that's it. So it means that this is the weight in order for us not to exceed the stress on the springs, which are supposedly allowable up to 20 KSI. And again, based on our analysis, the first one to be stressed is your spring here in your spring 2. Okay, so that is for helical springs. So if you have any question in this problem, okay, if you have any question in this problem, you can comment below, and then we will discuss that one on the live meeting. Okay, so thank you very much for watching. That is the end of our module 3.